Okay, so now that we have seen adding, subtracting, multiplying, and scalar multiplying with matrices, there's one operation left, and you might assume that it would be division because that's the only operation that we haven't used yet. However, it's not, but it's related. What's interesting about matrices is that you can't really divide them. However, there's just like with numbers, I'll give you an example with numbers here. If you had the number 24 and you wanted to divide that by 8, we know that that is equal to 3. But this division is really the same as multiplying by 1/8, right? Dividing by 8, multiplying by 1/8 gives you the same result. And so any division problem is really just multiplying by what we call the inverse, okay, or the reciprocal. Now in matrices we have a similar process. We know how to do multiplication with matrices, but we don't actually have a division. And so instead of dividing, we're going to be multiplying by the inverse, almost said reciprocal, multiplying by the inverse of the matrix. We just have to find what the inverse is. We also have to define what an inverse is. Okay, and so let's say matrix A is an n by n matrix. Okay, that's the first thing. It's got to be n by n. It's got to be a square matrix in order for this to work. All right. Now with a square matrix, n by n, if you knew its inverse, say A with this little -1 superscript, that's going to be your inverse notation. So A inverse, or A to the -1, is the inverse of A. Then we have this relationship that A times A inverse, anything multiplied by its own reciprocal or its own inverse, if you notice with real numbers here, if you multiply a number by its inverse, you should get 1. Well, in matrices, the equivalent of 1 is the identity matrix of the same size. Okay, so AA inverse is the identity matrix, and if you reverse the order there, A inverse A will also be the the identity matrix. Okay, so it doesn't matter the order. Generally, multiplication is not commutative, so if you switch the order, you typically will get different answers, but with inverses you don't. Inverses, you always get the identity. Okay, now there is a process for finding an inverse if you know the original matrix, and I'm going to actually show you, I don't know, 3 or 4 different ways to compute them. I'll give you a couple that I think are pretty quick. The one that your textbook is going to use, and I'll take an example here. Let's say find the inverse of, I'll give you this one that I like to use. It's the matrix 1, 2, 3, 4. Very simple, right? Okay, so that's the problem we're going to work with. So to do this, there are many different options. Okay, option number 1 is to take this matrix, use it as one part of an augmented matrix with the identity on the other side. So you essentially have two 2x2 matrices all crammed into one matrix. Now there's a reason this is important, and what we can do is we can use the reduced row echelon form that we've seen in the past to simplify this. Once this matrix is simplified, what you will end up with is the identity on the left side, and you will have the inverse matrix on the right. So if you start off with matrix A and then I sub n on the right, when you RREF, you'll end up with the identity on the left and the inverse on the right. So here, to find that reduced row echelon form, we can go to our calculator. Now, you could use row operations on this. I'm not going to have you go through all that to do that. We just go to our calculator. Let me get rid of that. And then you're going to go to edit, and we're going to want to turn this into a, notice this is 2 rows by 4 columns, so I'm going to go 2 by 4, and then I want 1, 2, 1, 0 as my first row, 3, 4, 0, 1 as my second row. And then if I go with the matrix menu over to math, down to RREF, go back into the matrix menu. This is should not be new stuff to you. Hopefully you nailed down this reduced row echelon form back in section 8.2. And here's our solution. Now our inverse matrix is on the right. Now I'm going to go ahead and put this in fraction form. I just like the look of it. There it is. I'm going to move that over to the side here, and we're going to get -2, 1, 3/2, and -1/2. Okay, so that would be the inverse matrix. So the inverse matrix is this matrix over here on the right. That right there is equal to A inverse. Okay, so that's one method. It's using the reduced row echelon form. Another method is to go to your calculator once again. This time you're going to type in the matrix 1, 2, 3, 4. And then on your calculator, let's get that typed in anyway. So we go second matrix over to edit, and this is a 2 by 2, right? So 2 by 2, and then 1, 2, 3, 4. All right. So I've got my matrix entered, but it's just this one. It does not have the identity on the right. It's just this single matrix. What you can do is on your calculator, the actual button that the matrix menu is on is this X inverse. If you go to the matrix menu, grab the matrix we just created, and hit that button, you'll see the little -1 show up. That will directly give you the inverse matrix. And of course, if you want to put that in fraction form, there you go. Okay, so your calculator will do that. Without having to go through a longer process. So that might be my favorite. Oh, at least it's the shortest probably. Okay, so that's option number 2. Option number 3, and this one actually is probably my favorite because I don't need the calculator. If I can avoid using the calculator, I do. With a 2 by 2 matrix, you can find the inverse simply by, let me write this a little bigger. 1, 2, 3, 4. Simply by swapping the 2 entries on the diagonal, then changing the sign, so you would multiply by a -1, changing the sign on the other 2 entries, multiply them both by -1, and then multiply the entire thing by the scalar 1 over the determinant. Okay, now this one seems a little bit complicated, but when you get the hang of it, it's pretty quick. First thing I would do is just calculate the determinant of this matrix. 1 times 4 is 4. 3 times 2 is 6. 4 minus 6 is -2, so that's the determinant. Okay, I'm going to keep that in mind. The inverse then is 1 over the determinant times, now if I swap these two, I get the 4 top left, the 1 bottom right, and then multiply each of those by a negative. And then if I distribute the -1/2 in, I should get -1/2 times 4 is -2. -1/2 times -2 is 1. -1/2 times -3 is +3/2. -1/2 times 1 is -1/2. And in theory, that should match up to the other answers that we got before. So here are 3 nice processes. They're not the only ones, I don't think, but they're the ones that I'm going to show you. I think if you have your calculator accessible, I think the second one is probably the best. It's fast, pretty fast. This third one here is fast if you don't have a calculator and you want to just do it by hand. And then number 1 here is the one that your textbook uses to reduce row echelon form. Actually, they go through, instead of using the calculator, they go through using the row operations there. Okay. Good. Next video we'll look at some larger matrices.